Hey guys, here is the notes, or here are the notes for section 7 and 8 of Unit 3. Section 7 is on isosceles and right triangle theorems. Section 8 is on altitudes, medians, and bisectors. We got about 6 or 5 slides. There's the sixth one's like a little puzzle, so we'll get there. But wanted to look again at an isosceles triangle. And the reason I know that this is an isosceles triangle is because we've got two congruent legs. Isosceles triangles have at least two congruent legs, and they have a base. Now the base is always across from the vertex angle up here at the top, would always be across from the base. The legs are always going to be across from the base angles. The base angles have to be touching the base. The vertex angle is not touching the base, it's across from the base. We do have an isosceles triangle theorem that says if two sides of a triangle are congruent, like we have here, two sides, this leg congruent to this leg, then the angles opposite those sides, the base angles, are also congruent. That's our isosceles triangle theorem. So if I look at example 1 down here, it says what are the measures of the base angles of the following triangle? Well, if I know that my vertex angle is 35.2 degrees, I can take that 35.2 and I can subtract it from 180. 180 minus 35.2 degrees. Oops. And if we subtract that, we would end up with, let's see, 180 minus 35.2 is going to give us 144.8. Now that 144.8 needs to be broken up into these two angles. This angle right here and this angle right here. And it has to be broken up evenly. So that means I can take that 144.8 and I can divide it by 2. I can just cut it in half. Take the 144.8, divide it by 2, you're going to get 72.4 degrees. So 72.4 is what each angle would have to be. That would be each base angle would be 72.4 degrees. Each base angle would be that amount. So if you add 72.4 plus another 72.4, these two added together plus the 35.2, that's going to add up to 180. And those two had to be the same because we know that these two angles were the same. Since the two angles are equal, since the two sides were equal, the two base angles had to be equal as well. That was example 1. Moving on, here's example 2 now. Let's take a look at this one. A cable corporation has installed an antenna perpendicular to the ground. So here's the antenna. It's perpendicular to the ground, so we know these are right angles. So let's take our little right angle and put that in there. Okay, so we know we're going to make a right angle to the ground. The antenna is held steady with guy wires. So these are guy wires that are holding this steady. There's one in the back that you can't see. There's 3 of them. And they're equal lengths. So I could automatically put that this guy wire is equal to this guy wire right here. Those are equal lengths. Are the guy wire anchors on the ground the same distance from the antenna? So what they're asking for is AC congruent to BC. They want us to see if those two are equal. So PA and PB are given to us as congruent. This is the guy wires are equal. It's also given to us that the antenna is perpendicular to the ground. So that's also a given statement. So since they're perpendicular, we could actually tell that the two angles have to be equal because perpendicular lines tell us that they have to both be 90 degrees. So since they're perpendicular, we can naturally conclude that they have to be equal. They have to both be 90 degrees. This piece was given. We could also say that PC equals itself. So I could actually put 2 tick marks right here to show that this length is congruent to itself. So I actually have a side here a side congruent to a side, and I have another side congruent to another side in the middle if I need it. I have angles down here. I also have got angle A congruent to angle B, because if you remember from the last slide, the isosceles theorem, that if two sides are equal, then the angles have to be equal. So if I know that these two sides are equal, that means that I can put an arc here for angle A, and I can put an arc here for angle B. That those two have to be equal. And that is an angle congruent to an angle. And I can also put another angle in the middle here where the right angles are. We know that these are both right angles. That's another angle congruent to another angle. So you might see already that we're going to have AAS theorem right here. Angle, angle, side. So because of this information, we could say that these two triangles are congruent. And it's because of angle, angle, side theorem. And because they're congruent, now I know for sure that this piece does equal this piece. That these two pieces on the bottom have to equal because corresponding parts of congruent triangles are congruent. Again, you don't have to write out the whole sentence, just use the 5 letters. But that's one that you have to do last. You can't do the corresponding parts of congruent triangles unless you already prove that triangles are congruent. Then you can say that congruent triangles are congruent here. So you have to do the triangles being congruent first, then you can use the CP/CTC. Moving on. The last way that we can show that triangles are congruent is called the HL theorem. And it's really, when you think about it, it's the only way that a bad word could work. I was telling you in class that we had SSS and SAS and ASA and AAS, and that the bad word never works. Well, if you don't call it an H and an L, and if you call it a side and an angle and a side, then you actually would have angle side side here, or side side angle. But it only works in right triangles, and it only works because we can call it an H and an L, because it's called hypotenuse and leg theorem. If a hypotenuse and a leg of a right triangle are congruent to the same in another triangle, and I should probably put here another right triangle, then the right triangles are congruent. So that's the only way that you could actually have a bad word there. You could have angle side side, but it's really not called that. It's called the HL theorem because it's got right angles. Right triangles have hypotenuse and leg. That's what a right triangle has. I should probably draw you a right triangle so that you could see that. Let me do that really quickly. We have a right triangle here, just so you know what the pieces are called. So we would put our little box in there to show that it's a right angle. Okay, now at the right angle, you've got two sides here. Those are called legs. Those are surrounding the right angle. The legs surround the right angle down here. Okay, across from the right angle, so in every single right triangle you find the right angle and you look across from it. And when you look across from it, you'll see the hypotenuse. So that's always where the hypotenuse will be. It's always going to be across from the right angle. So when I look at this right angle here, the hypotenuse is across and the leg is touching it. Hypotenuse and leg congruent to a different hypotenuse and leg. And actually, I should have put another tick mark down here, because those aren't all four the same. There's two here and there's two down here. Or there's one tick mark to one tick mark, two tick marks to two tick marks. So that would be called the HL theorem. That's another way that we can prove that two triangles are congruent. This one, though, has to be, since it's hypotenuse, has to be a right triangle. A perpendicular bisector is a segment that bisects another segment and is perpendicular to the other segment. We make the fish to make the perpendicular bisector. That means I made perpendicular lines. I can take my little box and I can put a little perpendicular right there, and I can put 2 tick marks because it cuts it exactly in half. So that we know is that if we draw this construction, then it's going to cut their segment in half and it's going to be perpendicular. Every side of a triangle has a perpendicular bisector. You could take a triangle, and it doesn't matter what size, what shape the triangle is, you could take a triangle and you could find the perpendicular bisector in each side. So let me show you just maybe a scalene triangle here. You would still have a line that you could find the perpendicular bisector of this side, you could find the perpendicular bisector of that side. I could find the perpendicular bisector of this side, it would be perpendicular and it would cut it in half. Every side of a triangle has a perpendicular bisector. And here's a theorem about perpendicular bisectors. It says any point on the perpendicular bisector is equidistant to the 2 endpoints of the segment. So any point that I want to put on this perpendicular bisector, let me show you something here. If I was to take a point and I was to put this point on my red line anywhere, I could put it there, I could put it way down here, I could put one over here, I could put one up here at the top. Anywhere, it's going to be the same distance from A as it is to B. That means that this distance from this point to A is the same as it is from this point to B. So from this point to A is the same distance as this point to B. This point to A is the same distance as this point to B. Same thing here. This point to A is the same distance as this point to B. Those are all the same distance. And guess what they're all making? They're all making isosceles triangles. Because this side has to equal this side, and you might see the triangle right here. So you have an isosceles triangle, and you have your right triangles inside, so you're cutting those isosceles triangles in half, making 2 congruent triangles. Here's another piece. This one's congruent to this one, so you know it's an isosceles triangle. So that's what the perpendicular bisectors do. It's equidistant from points A as it is to point B. Equidistant right there means the same distance. So it just says equidistance. It means equal distance. So equidistant you could put down as equal distance. It's the same distance as it is from one point to the other. That's equidistant. And the last slide here is called the angle bisector theorem. And it's almost the same as the last one. Any point on the angle bisector is going to be equidistant to the 2 sides of the triangle. So if I was to put a point here on the angle bisector, I could put a bunch of points. I mean, it doesn't matter. I could put points on here, as many as I want, and it's going to be the same distance from one side as it is to the other side. Now the only way this works is if you're using 90-degree angles. So you kind of have to use you got to go to them at 90 degrees, otherwise it's going to be way longer, way different. But if you're going at 90 degrees to both sides, it's going to make the exact same segment. So this one at 90 degrees would be the same as this one at 90 degrees. So you could put in your little 90-degree box to show that these are right angles. That means this distance would be the same as this distance. This distance here would be the same as this here. So again, they're going to make congruent triangles. These little triangles in here are congruent to each other because of the SAS theorem or whatever theorem we use. So that's angle bisector. Any point on an angle bisector is equidistant to both sides of the triangle. Again, equidistant meaning equal distance. And last but not least, there is a Mad Gab and a number stumper. You need to show me both answers on a piece of paper. Be the first one to do that, and you do get a prize. Here's your Mad Gab, and here is your number stumper. And you got to figure out what they mean. So I'm going to let you read it, look it over. You may have never heard of a Mad Gab, you may have heard of Mad Gabs. You may have never heard of a number stumper, you may have heard of a number stumper. If you can give me the correct answer for this and the correct answer for this on a piece of paper tomorrow, you get the prize. Good luck, and we'll see you guys tomorrow.